right now we talk about choosing the learners. What type of model to solve a particular problem is critical. And those learners here, and we say there's this complexity measure associated with learners. And we want to choose the right level of the complexity such that the model will not underfit nor overfit the training data sets. So always choose the right amount, right? So that's always the challenging part, how to choose the right sets of models. So in the context of the model we discussed so far, the linear regression models. So in the model we have, you can increase your feature space by including high order features, such as polynomial features. And the question is given that particular problem, what type of features should I include in my learners? And should I choose nth order polynomial or something bigger, right? 10s or 20s, what is the order of polynomial should I choose? Or should I use a more sophisticated model, right? Such as neural nets with more complex structures. So that's the question we think about how to solve this problem here. So in discussion this VC dimension here, we're going to focus on the problem of the classification problem. Let's think about that context, the classification problem. So in terms of a classification problem here, so we're going to have a metric here, right? So we're going to metric here to quantify the performance of the models of that. So the performance of the model, so right now we talk about the accuracy. So for now, we're going to make these assumptions just for the analysis purpose here. We assume your training data. We assume your training data is something called IID. So which means that the data itself are independently distributed, identically distributed from the samples. So you think about that, the data set you randomly pick up from the universe of all the possible pairs of X or Y, and you randomly pick up them, and there's no correlation between different training samples. So this is, of course, is the ideal situation, but it is necessary in order to carry out this kind of theoretical analysis. So usually we'll assume the training data set is something called IID here. More specifically, is independent, identically distributed samples here, follow the same distribution, some underlying same distribution. So previously, we already provided a metric to quantify the performance of any particular models. Suppose C star is your models. So your model here, giving me X here, and I will make a classification. Let's assume it's a binary classification. It's either 1 or 0, right? Something like that. And a given set of parameters, choice of that. And then you can measure the accuracy of the models in terms of this way. So, for instance, the accuracy model say, given the sample you have here from 1 to m, you have m number of samples, and you compare your predicted class level and compare that to the targeted class level. If it's true, if it's the same, and then which means you're making correct predictions. Otherwise, it's one mistake. And I'm going to use this indicator function to indicate that. So this is going to be a 1 if it is not equal, 0 if it is equal. So essentially indicate that this is a one mistake here. And you're going to average across all samples. And that will be the overall, the error rate of your prediction. And we call that training error. So that's what we talked about so far. Training error in terms of the accuracy. So in the context of this VC dimension discussion, we will call this training error called empirical risk, or just a terminology. People like to use this a little bit more fancy name to tell it. So that is called empirical risk, standing with REMP, empirical risk. So, so this is what you obtain from the training data. Of course, what we are more interested in is the performance on the entire collection data. And you think about the universe of the test data sets. So in that case, and essentially we're going to compare for each data sample from the test data sets here, we're going to compare its prediction from my models here to its actual target label, that ground truth of these data sets. And if it's it's different and contribute one mistake, otherwise not. So in that context here, we're going to do average instead of over this number of training samples here. We're going to do average over the entire collection of all possible test data you might want to see. So, so in that context, we use this notation called expectations here. So expectation, which means that this is the kind of error, This is the mistakes here calculated over the entire collections of the universe of the test data sets. And that is the test error performance. And we call it risk. So risk is this quantity we are interested in, because risk provides you a kind of a performance metric on the entire universe of possible samples. And but however, this number is unknown. We don't know this number. The reason we do not know because we do not know these underlying distributions here. And that distribution may be, we know there is a distribution, but we don't know what the distribution is. So for these reasons, we cannot collect the entire samples of the test data sets. So in the real applications here, somebody provides you some test data set, but that test data is still a subset of the entire universe of possible test data sets. So, for that reasons, and the performance metric you evaluate it on the given test sets may not be kind of representative of the entire data sets. So that's also a potential issue to that. In this context here, we are talking about the true error rate. This means that it is evaluated over the entire universe, all the possible pairs of samples. And we call this guys here R theta, called a risk. And this is the risk is the quantity we are interested in, because this is a true measure of the performance of the models. But of course, this is unknown. We don't know that. The number we know is this empirical risk. This is evaluation on the training data sets. So the question is always, people want to ask here, if R empirical is this one area I know, but however, can be calculated. R theta here cannot be calculated. However, this is a quantity I'm interested in. So eventually, I want to know this quantity. So the question people want to know, how, if I know this number here, how does this provide me information regarding the true risk, R theta here? And do you know what's the information I can say regarding R theta if I know the R empirical risk here? So, so how these two numbers are related here. So this is a tricky question, right? It's not easy to answer here. So because depends on your choice with the models here. So if you underfitting your models here, if your model underfitting your data sets, so for instance, your y and x relationship is very highly nonlinear, but you fit a very simple linear curve. So in that case, it's underfitting choice of that. So under that choice, your empirical risk, our empirical risk will be very similar to the risk. And as we say that, if you look at the learning curves or the performance curves, and these two are very similar. However, on the other side, if you are overfitting your training data sets, so in that case, your empirical risk will be much smaller than the actual risk here. Your actual risk could be much bigger than your empirical risk. So which means that your test error might be getting a lot worse because you are overfitting your training data sets. So essentially the questions everyone have always in our mind is, right? What's the relationship between empirical risk and the actual risk are there? So, so that came to this theory of the VC dimensions here. So the Vapnik and his collaborators came up with a metric, something called VC dimension. And let's call it H here. So there's this H number associated with one class of models. And for instance, a linear classifier, one class of models. And this is one number represent that class of models. And if you know the H, which means know the VC dimensions of the class of models, and then this mathematician proved that the difference between your test error here, so this is your empirical risk, and is going to be upper bounded by the empirical risk, plus a constant number here on the right-hand side here. Well, essentially what's saying that the difference between the test risk and the empirical risk here is going to be upper bounded by these numbers here, And that's what this VC dimension tells us. Well, so we're going to talk about how do we actually how is VC dimension is defined. So we're going to talk about that. But for now, let's look at this formula here to think about what does this mean here. So in general, what this means is, so first of all, I want to emphasize here, what this provides you here is this inequality. It's not an equality, it's an inequality. It's saying that the difference between this test error and the training error here, this difference in general, right? In general, we expect to be positive, right? Because we fit the model on the training data sets. So in general, you remember the curve, the performance of the curves here, right? So this is training and this is testing here. So in general, there's a gap between training and testing here. And this is a gap here. So in general, we expect these things to be positive. The question is, how big is this gap? If the gap is too large, such as in this side here, and so we know that the model is overfitting. We don't like that. We like the gap to be small. And this formula is saying that the gap here between the risk between the test error and training error here, the gap here is not larger than this numbers here. So that's what this is trying to say here. And in some way, this is something called upper bound. Upper bound number here. Well, let's look at this upper bound number here. This upper bound depends on a few factors here. And there's one number here is M. M is the number of training samples, right? So what this say here, you roughly scale as the square root, 1 over square root of the M. And this saying something like this, if you double the size of the training data sets, the bound here is going to be lower roughly with 1 over divided by square root of 2. So your bound will be shrink by square root of 2 if you double the size of the training data sets. So that's roughly what they're saying here, right? So that's also good, right? Essentially saying, if you increase your training data, and this gap here tend to be smaller, tend to shrink. And that's what we expected. The more training data sets here, the learning model is likely more realistic here. There's less issue of fitting. So that's what we expect. However, there's another numbers here. The another number is this eta. So this eta here is the same. The reason is this. So this gap here, it turns out that it's not a deterministic stuff. It's not deterministic because you cannot say for sure this is always true. What those theoreticians proved is that this is true only with high probability. So that's only they're saying here. So that's the reason you have this eta term saying that with high probability 1 over eta, and then that's true here. So this is something in general always when people in the study statistical learning theory, and there's always a formula in terms of this type of language here, because you cannot say deterministic. You can always say in a probabilistic sense. In saying that, well, suppose it is, let's say 0.001 here, essentially saying this with 99% probability, and then we can show that this gap is less than this side here. So that's what this means, right? All right, so this is okay. And this is something it's just a mathematical language to describe the bound here. And then what we want to focus on is this guys here, is this H numbers here. And that's what makes things interesting, this H number here. Right. So what this say, this is the H is the VC dimension here. So what this model is saying is the higher the H, the gap, the larger the gap in general. That's the case. The higher the VC dimension, the larger the gap. And which means if you want to make sure that these guys are gap is small, it's better to using a small H values. If your H is small, and then that's better. So H here, we'll talk about, we'll talk how this is defined here. Essentially provides you a measure of the complexity of the models. Complexity model. And under this kind of interpretation, what this means is this: the lower the complexity of models, the smaller is the gap. So that, that's what is consistent with our understanding. So lower the complex model, smaller the possible gap of that. If your model is very complex, which means you're going to have a very high VC dimension, so in that case, your training error is going to be maybe very different from your test error. So that's what this. Of course, this relates to both H and M here. you can compensate the effect H by increasing the sample size. So if your model H is very complex, and how do you make sure the gap is small? Well, one way you can do, you can increase the sample size. So that's what this means. All right, so let's talk about how the VC dimension is defined. So before we talk about that, we're going to talk about one definition here, the concept of the shattering. We say a classifier, in general, a classifier can shatter points x1 and xh here, can shatter h points if and only if for all these points here, this classifier can achieve zero error on the training data sets here. So what does this mean here? This means this, right? Suppose you provided with a collections of data sets here, each number of data sets here, and we say a classifier can shatter this data point if you can assign any labels to this data set here. If you, for any label assignment on this data sets here, you can always learn a classifier such that can perfectly classify these data sets here. And that's what means of the shattering. So remember in this case, the shattering is only respect the data. There's no labels. The reason there's no labels because in order to claim this classifier can shatter this point here, which means you are allowed to assign any arbitrary labels on these data sets here and for any combinations. You want to make sure that for any combination labeled on these data sets here, your classifier should be able to successfully classify them. So that means the shattering here. So for instance, let's take examples here. Suppose let's talk about this linear classifier, perception type of classifier here, and the two dimension. This is the x1, this is the x2 here, and you have three parameters. That will be the so that will be a no. So that will be a no. This is actually the yeah. This will be three parameters here. So the question is this, right? How can this classifier shatter these data points here by choosing certain parameters here? You're allowed to choose the parameters associated with these models there. Well, so let's think about it. Let's check that, right? How do we verify if this is the case? Well, let's just do it, right? I have this two data sets that's fixed here. However, I'm allowed to assign any arbitrary label, class label to them. For two data sets here, if I think about binary classification, overall, there are total possible 4 possible label assignment on these two data sets here, right? For them, so that could be both. It could be -1, 1 here, could be +1, -1, and both of them are +1, both of them are -1. So that's 4 possible label assignment for that two data sets. And then we just want to say for each scenarios here, whether we can come up with a model to correctly predict this label assignment. So for this data set here, it turns out it's possible, right? Because that's very easy to see. And for this data set here, I can select a classifier to be along this slope here, point in this directions. And if everything above, I say it is -1, everything below, I say +1 here. Right? And so you can do that. You can correctly by choosing this parameter θ0, θ1, θ2, you can correctly separate these two data points, no matter the choice of the label assignment. And for this reason, and then we say this classifier, this particular classifier with these 3 parameters can shatter these two data points. Okay, so that's called shattering. So let's take another example here. Suppose now, again, we'll consider shattering of these 2 points here. However, in this case, here we'll consider another model. So in this model is a quadratic model, is a circle. Essentially, if this model, there's only 1 parameter associated with this model here. This model is saying that, well, if the only parameter is to determine the square radius of these circles here, if it's within the square radius, I'm going to assign label with -1, with +1. Otherwise, I'm going to assign outside, I assign label with +1 here. So the question is this: can this model shatter these 2 points here? Well, again, let's check that. So there are 4 possibilities. And again, there's 4 label assignment. This 1, 2, 3, and 4 here. All right. So let's think about that, right? So for this cases here, let's think about the right-hand side here. Well, if I choose a radius to be small here, and everything inside would be everything inside here would be a negative label here, -1 here. Everything outside would be +1. Right? So in that case, well, because I have two red dots here, +1, I can correctly classify them. So now we'll move on this side here. So both of them are -1 and -1 here. So both of them are -1. Okay. So however, I can increase the radius, should the new mu here, square root of mu here, such that now outside is to be +1, inside to be -1. So again, I can correctly set assign labels of -1 to these two data sets here. And similarly, on this one, you can do it. However, you cannot do it on these examples here. So in this case here, what do you have here? The red dot is +1, right? Remember that. And this guy here is -1. So no matter what values the radius you choose, you cannot achieve something such that red dots become inside the circle and the blue dots become outside the circle. It's just impossible to do. So for these reasons, and we know that, we conclude that this classifier here cannot shatter these 2 points. And that's the definition of shattering here. All right. So, and then now came to the dimension, VC dimension, once we understand the concept of shattering. So VC dimension is defined as the maximum number of points. The maximum number of points.
The previous slide.
That can be shattered, can be arranged, maximum points can be arranged such that fx can shatter them. So that is the definition of VC dimension. So your VC dimension here, so one thing is this, the VC dimension only cares about the number of points, maximum number of points that can be shattered. And then you can choose any arbitrary choice of points. So that will be left to you. You can choose whatever the points you want, as long as you can demonstrate that this given set of points can be shattered by these models. And then you know that VC dimension is at least this number here. And so in determining the VC dimension here, you can think about is a kind of it's a two-player games here. So your model is fixed here with a certain number of parameters here. So that parameter, you learn those parameters based on particular choice of label assignment on this data set. So one player is doing something like this. I'm going to choose the locations of these H data points. Right? So there's one player. I can always choose the location data points here. And then the second player will be try to assign target label on this data points. And then player will do it again, try to learning the parameter based on these target labels. Right? That's kind of two-player games of that. So if this classifier can reproduce the target labels, and then the player one wins. Right? Player one wins. So the player one is always trying to identify a set of locations, and he or she expect that no matter how you're going to change labels, the classifier can always correctly label them. So it's so important that to choose the optimal choice of this H point such that class label, for any choice of class label, you can predict them. The player two, the point is this, right? If you give me the particular choice of a location data points here, I will try to assign you the most challenging target label such that you fail to classify them. So this is always two-player games of that. So in a mathematical language saying this, right? So what is the VC dimension here? Essentially that for exist, so you have to exist, you have to identify that optimal H data points for exists this H data points such that for any choice of class labels, there always exists the parameters such that you can correctly classify them. And if that's the case, and then you know that your VC dimension is at least H. And of course, the definition of VC dimension is the maximum number of H data points you can possibly identify such that they can be shattered. So that is the VC dimension here. So let's look at these examples here. So look about this example, right? This classifier here within the circle, this -1, outside circle is +1 here. So what is the VC dimensions of this classifier here? Zero-centered circle. So what is the VC dimension of zero-centered circle? Parameter choice will be the radius. You can choose that. And however, we already know that what we
Hey,
cannot.
Professor, I've got a question regarding 2 slides ago,
Okay.
the one with the circles.
Let's do. Can we do this again? Yeah.
No, not this slide, the one 3 slides before this one.
This one.
Yes, this one, yeah.
Yeah.
The part with the red box, how is it that you can't just decrease the radius and make it work?
Yeah. So you mean for the red box, why we cannot assign the correct label? That's your question asking about. Is that right?
Yeah.
Okay. So the reason is this: if you look at this classifier, if you look at this ones here, so this classifier is saying this. If I'm going to extend this side here, saying this, you're going to assign sign to be +1 if essentially the radius x1 plus x, if this radius here, with the radius here is less than mu, is greater than mu, sorry, greater than mu. And if it's -1, if this is less than mu. So if it's inside this radius and then it's -1, it's outside is +1. So now you think about this. I have 2 data sets here, and this is +1, this is -1. And which radius you can choose to achieve that goal? Well, you cannot, right? In order to make this blue dots inside, so your radius is going to be at least this size here. Radius must be greater than this guy in order to make this blue dots inside. However, as long as the radius is greater than this, you know that your red dot is going to be inside the circle as well.
Oh, I see. Just because the red dot's closer to the center.
Yeah, that's right. Because the red dot is closer to the blue dots here, just so you cannot share these 2 points here.
Okay, thank you.
All right. So in that example, I just show you that so that these 2 points you cannot share them. And the question is, can you identify another 2 locations of 2 points so that you may be able to shatter? So that's the question. Okay, can you maybe not these 2 data points here? Maybe I pick up another data point here. Maybe this one's here. Maybe this here. Can you do that? It turns out you cannot do it. No matter where do you place these 2 data points, I can always identify that example such that the classifier will fail to correctly classify them. And for that reasons, then we know that the VC dimension cannot be 2, because I cannot identify 2 points such that I can shatter them. And then, however, for 1 data point, of course, you can do it. And for these reasons, for these models here, the VC dimension will be 1. Okay, so that's the VC dimension for this example here. So now let's go back to for the linear models here. So what is the VC dimension for this model, or this model here? All right, so what we concluded so far is this. We know that for 2 data points, in the previous example, we showed that this classifier can shatter 2 data points. And so for that reasons, we know that the VC dimension is at least 2. So we don't know the values yet, but for now, I know that at least it is 2. And the next number I'm going to try to verify is whether this classifier can shatter 3 points. If we can shatter 3 data points, then I can conclude that VC dimension is going to be at least 3. So let's verify that. So what about the VC dimension 3 here? So remember, I'm going to say offer these 3 data points here. For these 3 data points here, what I'm going to do is this. Now I have the location 3 data points. So now you can assign any arbitrary labels to these 3 data points. So in this case here, you'll be +1, +1, -1. Well, so in that case, I say I have lines here, I can separate them. And you might want to say, give me another examples here. Maybe you give me another example, another class label. So this is a red here, this is a blue here. So suppose I want to assign them with different colors. And let's say this is red here. Well, so in that case, you can come up with a line to separate them as well. So on this side here, right? So you can do that. So you can verify by yourself, no matter how you assign labels, for this choice of 3 data points, I can shatter it through this linear classifier. And for this reason, we said that this dimension is at least 3. So at least 3. So the next question is this. Can this VC dimension be greater than 3? And that is a slightly harder question here. Can the VC dimension be 4 here? Well, suppose you give me the 4 data points like this one here. And well, I can provide you a class label assignment to be something like this. I can assign this to be red here and assign these two to be blue. So now, given this label assignment, you know that there's no linear classifier can separate these 2 group data points, and it fails to do that. So no, so for that reason, we know it cannot be these 4 data points. Well, you might want to try, let's say you want to try, well, let's try other data points, 4 data points here. You might want to say, well, I have 4 data points here, maybe I organize it in this way, right? And in some other strange structure of that. Well, you give me that, I can always tell you, you cannot do it. So I might want to say 2 red here, and then I have a 2 blue here. And in that case, you can also fail to correctly classify them. It turns out that no matter what 4 points you place on this plane here, and then I can always find out the class label such that this model cannot correctly classify them. And for that reason, and then which means that VC dimension cannot be 4. So as a result, the VC dimension turns out to be exactly equal to 3 for this model. Right.
For VC dimension equals to 4, you placed all 4 of them in a straight line. What if you placed all 3 of them in a straight line for VC dimension equals to 3?
Yeah, that's right. So that's a good point. Let me make that point here. So this is a good question here. So so the question here is this, right? Suppose for 3 here, and I can do this, right? For 3 data points, suppose I pick up 3 data points here, look like this on a line here. Well, so in that case here, if I have label assignment look like this, so in that case, the model will not be able to correctly label these 3 data points, even for the 3 data points here, okay? So which means the model cannot shatter these data points here. Okay, so that's correct statement. So that is the reason in the VC dimension here is important that it's not ask you say to shatter all possible organization 3 points. You only say that as long as you can pick up any choice of the points and your model can shatter it, and then that's okay. So the game here is this. So that's the reason you have this game here. You know, you choose the location. You can choose whatever location you want to be. And you can choose to be all line and in a line, along a line. So that would be a poor choice because it reduces the number of points that can be shattered. So you always want to maximize the choice such that place the optimal choice such that you can achieve the maximum number of points can be shattered. So this is a choice. Does not mean that for any choice of 3 points, the model can shatter it. So that's the point here. So however, when I make the statement and say the VC dimension, it cannot be greater or equal than 4, which means that you have to verify all possible locations of 4 points, all possible choices. Essentially, you exhaustively tried all possible 4 points, and I cannot find 4 data points this model can shatter. And so you can see that to verify the VC dimension is not greater or equal than 4, you need to make more efforts because you have to try all possible choices of that. However, just to make a statement say, I want to say the VC dimension is at least something, and then that's actually is easier because I'm just going to propose a specific the 3 points here, and I demonstrate they can share, and then you can succeed for doing that. So that's the VC dimension. In general, VC dimension, you can see it's not as something easy to calculate because you have to make sure that it doesn't exist points here, and then you can share them. So that's the concept. It's a concept. It's a very useful concept, but does not necessarily mean that you can easily calculate them. All right. So in general, so this is what I talked about so far here. For this 2-dimensional data sets here involves 3 parameters, mu1, mu2, mu0, or theta1, theta2, theta0, 3 parameters for two-dimensional features. And then the VC dimension is 3, okay? So that's okay. But in general, if you have n features, so in that case, your model would be fx here. I'm going to use theta here to represent what we did previously. You have a sine function, whether this is greater or positive than 0, it would be theta 0 plus theta 1 times x1 plus theta n times xn here. So that's the linear classifier for n-dimensional input features we talked about here. So we have n coefficients here plus 1 intercept. So overall, you have n plus 1 parameters. So it turns out that you can prove it. I will not prove it here, but you can prove it. It turns out that the VC dimension of this models here is exactly equal to n plus 1 for the linear models. And so that's a very nice thing to know. So, and also coincide with the number of parameters within the models. And do you remember we mentioned this, right? When we say the performance of the model, and you can be you can plot them as a function of the complexity of the model. So at that time, it's kind of hard to measure complexity, but we say, well, you can think about the number of parameters within the models. So it turns out for the linear model, that's actually a reasonable way to measure complexity, because the VC dimension is exactly equal to the number of parameters you have. However, in general, that is not true. The VC dimension does not necessarily equal to the number of parameters. In general, this is not true. So it provides you a measure of the power of the learners, how complex kind of type of a decision boundary this learner can learn. So so provides you the higher the VC dimension, the more power is this particular models here. So, so this is very important. Number of parameters does not necessarily equal to complexity here. In fact, you can define a classifier with lots of parameters, but not much power. So I'll give you examples later on part of that. And you can also define one classifier with 1 parameter, but with lots of powers here. So that's also possible. So let's take one example here. So this is a one kind of a classifier for 1-dimensional data sets here with only 1 parameters here. And the parameter here is essentially this t here. T is your parameter. And in this model, it's saying something like this. It's going to be labeled with 1 on this 1-dimensional axis if it's within this boundary there, otherwise it's going to be 0. So, so the question, what is the VC dimensions of this model here? So this model has only 1 parameter. And we can demonstrate that this dimension is at least 3. So why this is the case? Well, so I pick up these 3 data points here. 1 is 0, x2 is something slightly less than 1, x2 here. So that's 3 data points. I can label these 3 data points arbitrary ways. So that will be all possible, 8 possible combinations of the label assignment on these 3 samples here. And this is all 0, this is 2, 1, and 1, 0. And you can see that you can choose this parameter such that it can correctly classify all 8 possible choice label assignment. And for that reason, and we know that the VC dimension of this class of this model here is at least 3. So it's going to be greater than 3, greater or equal than 3, at least 3. And then once you demonstrate it here, and then you move on to say, is this going to be, can this be 4? And it turns out it cannot. So I will not demonstrate that, but if you want, you can try that out. So no matter what 4 points you place, there's always some label assignment, you cannot do it. So, the point I want to make through this example is this. So in this example here, you only have 1 parameter here. However, the VC dimension is 3. So the VC dimension is not equal to the number of parameters. All right. So once we have the VC dimensions here, and how this will be useful. So, so this will be useful in some way. People propose it for model selection. So why is that? Because VC dimension, that will relate to the formula we talked about so far. The formula we say is, if you know the VC dimensions of the models here, and then you know roughly the upper bound of the test error of your models, And the smaller the gap is, the smaller this value is, the upper bound gap here, you know that your test error cannot be greater than this number here. So for these reasons here, it provides you some guidance in terms of for you to estimate the performance of your test data on the test data sets here, right? So if this is useful, certainly that would be great, fantastic, because you do not need to do cross-validation, you know for sure what's the test performance. So that would be the ideal situation. And that is also the reason why people kind of interested in this type of the models theory here, because it might be provide you more principled way to measure the performance of your model on unknown test data sets here. And so we know that previously, in order to quantify this stuff here, what we did previously is this. So, suppose you have a model here with 6 possible choices of the parameters here, 4 different, let's say 6 possible models here. And what we did last time in order to choose which model should I use? And then what we did last time is say, well, we're going to do training and validations here. So you're going to measure performance on the training area. And then once you learn the parameters and models, and then you evaluate the performance on the validation data sets. So you have both training area and validation area. So then we say I'm going to pick up the performance on the smallest validation area. And so we say that is our best model. And now, once you have the VC dimensions here, and one idea is that you might not need to carry out this validation performance anymore, because there are some disadvantages associated with the validation strategy here, right? First of all, in general, we do not have a test data set available. In order to measure the validation performance, what we need to do, we need to split the training data into 2 piles. One used for training, another used for validation. And for that purpose, once you split them, and you're going to reduce the number of samples that can be used for training the model. So that you lose some power for doing that. But secondly, and this validation areas here, it might be biased, might not reflect the true performance of the models, because your models here is evaluated based on this validation data set. They might be small. Because of small, they're not representative of the entire and true space of the test data set. So you can see that could potentially some of the limitations associated with this method here. And however, if the VC dimension, if it's great stuff, if the bound here is very tight, very good, and then what you can do is this, and you can evaluate your models on the training areas here, and then you can calculate the VC term. This is, do you remember the term on that formula? Involves VC and the number of samples, and let's call that VC term. And by add these 2 terms together, you get the VC test bound here. And this bound says that your test error is going to be not bigger than this guy's here. Not bigger than this guy. Your test error here is going to can only be smaller than this guy's here. So if you know that, so if you pick up the best performance based on this guy's here, F3 here, if you this test error here, if you calculate for some reason here, if test error, I give you a number here, is only 0.5. If that's the case, and then you know for sure that your test performance is going to be at least 95% accuracy. So that's very good. That tells you, very theoretical guarantees of the performance of your model. If this is the case, right? I make sure that if this is the case, if this number is very small, and which means that if your bound here is very tight, and in that case, this is that's a very good metric here. And then other people propose to minimize the models here, choosing the models here by minimizing these terms altogether here. Not only you have a training errors here, and plus additional term that's from the VC terms here. And this type of framework is called a structural risk minimization, SRM. So which means that when you minimize your models here, not only you minimize your training performance, but you can regularize the model through this additional VC terms of that. And but however, using VC dimensions here, to select complexity and based on the bound test error estimate. So however, there are other alternatives. I should mention that. So in fact, choosing VC dimension this way, and it's not very frequently used. And in practice, many people are using some other methodologies, right? For instance, there's something we already encountered. We calculate the likelihood under the models, because the likelihood sometimes the distribution, sometimes the number tells you something about how good is your model, how that can be generalized. So that's kind of not explicit, but kind of inherent, the kind of implicit way to describe the ability of the model. And then there's a few other things here that was used very frequently in this community. One is called AKK information criteria. So in this case here, what do? You minimize your loss function. So you have a loss function here, and then plus minus the number of parameters here. So in the previous examples here, you regulate through the VC dimension term. But in the AIC criteria, it's saying, I want to reduce, I want to have penalize the total number of parameters in my models here. So if you have a good training performance, and also at the same time, a smaller number of parameters, and this type of models is preferred, then the model with similar training performance, but a high number of parameters. So essentially, you penalize the number of parameters within the model. And there's another extension of that called a BIC, called a Bayesian information criterion. So in that case, you penalize not the total number of parameters, but instead penalize with the number of parameters times log of the M here. So log of the M is the number of samples. So essentially it's saying, compensate, take the number of training samples into account. So these are all this kind of, some of the heuristic methodology people propose that to do model selection that does not using cross-validation, but purely based on some measurement of the complexity of the models here. So similar to something like this, you have two parts. One is the performance part, and the second part is this penalty part. And the penalty part, based on VC dimension, that is the VC term, but you can think about in terms of number of parameters, or the number of parameters times the number of samples, based on different criteria. So in general, I should mention that all the method here is very conservative. They're all conservative. So what does this mean? It means this. So it goes back to this model, goes back to the, let's go back to this equations here. So it's very now advanced now in this equation here. So what happened to this? So remember that this is the formula here, only tells you the upper bound here. It's saying this, the test area is not bigger than this guy's here. So I give you examples here. So it's actually very common here. So suppose say your training area here, you get a 10% training area. So that's, you learn from models. And you say, well, overall, I can achieve 90% accuracy of that. And I want to know now, for this models here, how good is this test performance? Is test area is going to be 15%, like slightly worse, or is going to be 80%? It's going to be very worse. Which number it is? And then what if you calculate this bound here? So now, if this numbers here is small, so suppose this number here is 15% here, 0.5. Let's do that. So suppose this number here is 0.5, and then that's good, and you're fortunate, because you know for sure now your test performance is not going to be greater than 15%. And that is a very good case, and which means the difference between test error from the left, between the left side and the right hand side is very small. Even though I have an inequality here, but they are very close. And in that case, we say the bound is very tight, very tight. And if this is the case, and this model will be very useful. However, in general, in reality, this bound is very loose in general. So which means the difference between left side and the right hand can be very large. And then you won't be surprised if somebody tells you, say, the bound here is not 0.5, but instead it's 0.6 here, right? So in that case, what this says, your test error is less than 60%. Well, this is good to know, but it's not informative. Because my test error is less than 50%, which means does this suggest my model is good? No, it's not, doesn't, right? It's because the error rate is way too high. The reason way too high is this statement here, less than 50% error rate, is a correct statement, but it's not a useful statement. And so for that reason here, in general, the bound here is pretty loose here. And for that reasons here, this model, even though theoretically speaking, is an interesting concept, but practically speaking, it's not very useful. But theoretically speaking, it is a good concept here because it provides you a very interesting way to measure the complexity of the models. So for that reason, it's interesting. All right. So that's regarding the VC dimensions here. I think so. That's what I want to say regarding VC dimension. I did that very quickly because I think it's an interesting concept. But in practice, I think people rarely use VC dimension to select models. But instead, we still resort to kind of very simple and simple approaches based on cross-validation. Choosing models, choosing hyperparameters. I think this is also still recommended approaches here. And however, I think it's good to know some of the theoretical foundations in the field of the statistical machine learning theory, statistical learning theory, and what people think about. And then I think about it in terms of this type of concepts. All right, so this is what I want to say regarding VC dimension. And let me pause here for a couple of minutes to see if you guys have any questions. If not, I will switch gear, talk about new topic.
Professor, how is the term eta calculated here? Like, is that dependent on the model, or like how does that come into the picture?
Yeah, the eta here is introduced because it's a mathematical language to describe these things here. So it doesn't really matter here because it's just saying this, right? With eta here, with you choose a numbers here, what the confidence level you want to have here, and then you plug this number. So this term does not really matter that much here. So you just say, what confidence level, what probability, and then you will be able to state that bounds. So what matters most in terms of affecting the behavior of the model is this H numbers here.
Okay, so if we have a smaller eta, that means that we are trying to trade off on our probability, but that also
correct. So think about this way. Suppose you choose small eta here. If a small eta, let's say eta is 0.001, essentially I want to make sure the bound here is correct with extremely high probability. Remember this, right? Because the statement here is fundamentally is a stochastic statement, probabilistic statement, because your training area depends on your particular samples of the data sets, of the M data set. So that sample can vary dramatically. If you choose this sample different from the other sample, that give you very different behaviors there. So fundamentally is a probabilistic statement. And this one saying this, right? So with to what extent this is true, and that's when you have this probabilistic statement here. So what if you choose eta to be 0.001, and then which means the statement here is true, is 99.9% of the time. It's a very high probability that is correct and the statement is true. And however, you came up with a cost here. You need to, the bound here is going to be, the gap is bigger, right? Gap is bigger. So there is a trade-off between the two. In order to say with a high probability, and then this upper bound is going to be increases, it's bigger. So, so it's not that useful. All right, so that's VC dimensions here. So next, I'm going to talk about another set of models called a SVM, and support vector machine. So the support vector machine initially was actually somewhat motivated from the consideration statistical learning theory community, and then the VC. We're going to talk about this methodology, and this methodology has a lot of interesting properties, and in fact, you can somewhat calculate VC dimensions of these support vector machines, and you demonstrate that the VC dimension can be controlled. So that's the interesting properties of that. So right now, what we talk about here, if we have a linear classifier here, the VC dimension is n plus 1, the number of parameters, dimension plus 1, that's the VC dimension. However, you can reduce the VC dimensions of linear classifier by controlling its property, by narrowing its space. And that was done through this support vector machine. So that, you see, there is some theoretical foundations, and in some way makes the VC dimensions useful. So however, when we talk about it here, we will not kind of go back and revisit the VC dimension, but we're going to talk about motivation on the developing this method here. And you will see makes a lot of sense for this methodology here, right? So we're going to talk, so this part here involves some math. I just to give you some warning here, and it involves some math in particular related to optimization. So we will try to go it slowly. If you have any questions, I'll be happy to slow down and talk about that. So this is just give you a warning there. So first, I'm going to talk about give you an introduction. What is a support vector machine? And then we're going to talk about how do you solve these problems. And then talk about generalize to a nonlinear classifier using something called a kernel trick. And that will be later part of that. But first, today we're going to talk about support vector machine itself. So support vector machine, and it can be viewed as a linear classifier. So this goes back to the questions we proposed a while ago. And suppose you have these two groups of data sets here, and one shows on the left side here. The data set is the same. However, I have two different classifier here. And one classifier is this one here, and the other classifier is this one here. You have two different decision boundaries. The question is this: which one is better? Which one is better? And then we talked about last time, we said, well, we will prefer the one on the right side of that. And the reason why this is the case, because we thought, well, if I could imagine I can collect some test data sets here, something like this guy's here. And then I have other test data that look like this guy's here. Something like that, like a neighborhood, small perturbation, surroundings, labels of that. And if that's the case, you can see that the classifier on the left side will fail on some of this test data sets here. And however, on this right-hand side here, it still has no problems on the right-hand side. If you make small perturbation data points here, the classifier on the right-hand side can still classify without any problems. And then for that reason, we believe, intuitively speaking, the decision boundary on the right-hand side is better, right? So the question is, how do we do this one here? And previously, and we say that what we do is we can formulate some loss functions, such that we encourage this type of solution than this type of solutions. And the loss function we introduced for the binary classification problem using such as the cross entropy, the loss function. And you can, in fact, you can show that this type of solution will have a lower cross entropy than the solution on the left side of that. So for that reason, if you use the cross entropy, we'll prefer this type of models. So that's good, right? By using this type of loss function, it somewhat provides you a solution here, but didn't address the question, but didn't directly address this question here. So I would like to directly address this question and say, given these two solutions here, which one is better? And then can I come up with a metric to say which one is better? So that's something what this SVM model is trying to do. So one possible answer is this: SVM model is trying to say, and using this project here, trying to say, once I have the decision boundaries here, I want to roughly have some idea is this, what is this gap between these two group of data points here? So this is one group of data points here, this is another group on here. What is the gap between them? What are the distance that's separating, maximally push these two data points away? And so this is something called margins. So we're going to talk about today how to calculate this margins and then think about how to optimize it. All right, so that would be this slide's goal is here is try to think about the concept of margins here. So for that purpose here, we're going to change the notations here because in the SVM, we use slightly different notations here. So that's previous notation, right? We use the parameter theta, and then we intercept bias theta 0 and theta and so on. So we're going to change that to a new notation here to be B, to be the bias term, and then use W1 to be the coefficient. The reason we do that is because for some reason, historically, in the SVM, people use this WB notations for that. So you can also write down them in terms of vector representation. So that will be W dot X here. So the inner product between W and X plus this bias term B. So the parameter will be both W and B. So within the SVM, we treat them, explicitly separate them here. So in our previous model, we merge theta 0 with other parameters. And we say we don't need to address them explicitly. However, in the SVM, we do consider them completely separate, deal with them kind of separate. So that's the reason we try to emphasize using this notation here. Right? So in the models right now, previously we have said, we're going to calculate this linear response here, depending on whether this is greater than 0 or less than 0. We're going to classify a label to be 1 or 0. And within SVM, we're going to using this +1 labels if this is positive, and use the -1 label if this is negative here. And so that's the another notational change we're going to use for the SVM models here. So if this is less than 0, we say it's labeled -1. If this is greater than 0, it's labeled +1 here. Yeah. So in this type of linear models here, and we know there's one thing here. There's this kind of there's this redundancy in the model. So what I mean the redundancy model here is this. Well, I have the Wx plus B here. Suppose now I double the values of W, double the values of B. Will that change my classifier? Well, if I do that, if I'm going to do 2 times this guy's here, 2 times this guy's here, 2 times this guy's here, you can see that it does not change the decision process here. And if you double the values of W, double the values B simultaneously, the decision still stays the same because I only look at the values greater than 0 or less than 0. And for that reason, this WB here, there's a redundancy in these parameters here, and it's not completely determined. And for that purpose, we're going to fix that. We're going to fix those redundancies here by requiring and something like this. So we're going to have this models here, W equal to W dot X here plus B. However, we're going to say this. For all the dots, that is on this positive region here, we require them, this linear things here, to be greater than 1. On the other hand, if this numbers here is on the negative labels here, we require them to be less than -1. So that's the difference here. We're going to use +1 and -1, fix these 2 values. The reason we fix these 2 values here, such that this WB exact numbers is going to be fixed here. We do not have this scaling redundancy anymore, right? Because previously I can multiply by a constant positive number that does not change my decision. And I want to remove this scale invariance here by using this trick here. It's saying this, well, I have this fx equal to 0, but I want to make sure that all the data labeled with +1 here has values is going to be greater than, so in this case here, W dot X plus B on this side here will be greater or less or equal than 1. So that's one side of that. Dot X plus B is greater or equal than 1. And then this side here will be, say, if your data is on the label with -1, I want to make sure all of them to be W dot X plus B is less than -1. So that's the only difference I'm going to introduce here to remove this scaling invariance for that, okay? Right, so, but the problem stays the same here. So I have this parameter Wx. I want to make sure that for all the data labeled with 1, I want to make sure that they are above this plane here, this planes here, above this planes here. So I'm going to call that red planes here. I want them above this guys here. And then for all the data that's to be labeled with -1, I want to make sure they are below this planes, less or equal than -1. And this is a set of the problem here. No, I didn't do anything, anything new here. The only thing we use this fix to be +1, -1 to reduce redundancy. This one choice 1 is not important. You could choose 1 here to be 2, and it would be greater than 2 or less than 2. That's okay too. However, just for the convention here, we choose to be 1 here, greater than 1, and less than 1, okay? So that's what we're gonna do here. So next, what are we gonna do here? We're gonna calculate what is the margin between these two lines, two separating lines here. And when I say what's the distance from this point here to here. And this, again, this is the kind of a concept of separation between these two group of data points. And that's what we call the margin. When we calculate these margins here. And how do you calculate these margins here? Well, so that will be involved a little bit of geometry here. So we're going to go through them here. So right now, remember that this lines here is described by this guys here, by w dot x plus b equal to 1. This is this separating boundary, separating planes here. And this guys here is described by w x plus b equal to -1. So this is all the dots located in the dashed line, in the blue dashed lines here, is going to be described by this. And now we want to calculate the distance between these two planes. So these two planes are only shifting from one side to the other side. So they're parallel to each other. And so that when you have parallel planes, you can calculate the distance between them here. And that is the margin we can try to calculate here. First of all, let's determine what is this direction. Suppose I want to go from this to here. What's the direction what is the direction that is perpendicular to this plane here, to this line in 2 dimensions? In 3 dimensions would be a plane. What is the line that is perpendicular to this line here? Well, what do we know this, right? If you look at this data set here, if we take 2 data sets, this is w dot x plus b equal to 0. And we know that this w here is a normal vector. If you learn from the geometry, that normal vector w itself is perpendicular to this lines of that, because it's a normal vector. The reason you can actually show it, how do you show that? Well, you take 2 dots from this planes here, and one is x here, the other one is x prime. 2 of them here, one is x prime. They are here. This is x, this is x prime here. So now you can see that. Now take the difference between them, you conclude that w times x minus x prime is equal to 0, which means that w is orthogonal to this difference between x prime and x here. And that's reason w is a normal vector, is a vector perpendicular to the boundaries of that. All right, so that's first thing I want to do here. So I know whatever the boundary I want to draw from here to here, and then that is going to be along the directions of w. So that's the first thing I want to do here. So let's do this one here. Along the directions of w. So that's good. So next thing I'm going to do here, let's suppose I pick up 2 points here. Pick up, say, I call that, let's see, I call it x minus here. I call this data set x minus. Arbitrary from this point here, x minus here. I call this data set here, I call it the x plus. So I'm going to pick up x plus from this two planes here. From this side here, I call it x plus, and this side here, I call it x minus here. And let's pick up these 2 data points here. Well, so I know one thing I know now. So first of all, because x plus is from this wx plus b equal to 1, so I know this w dot x plus b is going to be equal to 1. So that's one thing I know for sure. Similarly, I know that w dot x minus, because minus x is located within this plane here, plus b is going to be equal to -1. So that's one thing I know for sure. Okay. So based on these 2 here, and we know that if we subtract them, we know that w times x plus minus x minus here equal to 2. If we subtract these two equations. So and this guys here is w plus minus x prime here, and this line's in that, and this guys here is x plus minus x minus. And then we want to calculate the length of this guys here. And however, let's check here. Let's assume x plus and minus here, because it's going to be along the direction of w here, the normal vector of that. Let's suppose this is equal to a factor. Let's say I call that a factor to be r here, to be r times w, because it has to be along the directions of the normal vector, the orthogonal to this guys, right? But however, I don't know the coefficient r here. That's something I need to determine that. Well, however, I'm going to plug into this equation here, and I can know that w times dot R W here is equal to 2. So which means you conclude that this coefficient R here is going to equal to 2 divided by the norms W squared, because the dot product of W with each cell is equal to the length of the squares, length of W's and square of them. And that's the norm square. This is R. Okay, I'm very close now. Right now, what I have is this. I know this, I know the X minus X now is equal to R times this. And the margins here, the margin, so this is the quantity I'm interested in. The margins here is going to equal to the length of the X plus minus X minus here, because that's this guy's here, right? This is the X plus minus X minus here. And that's the length here. And I want to calculate the length. What is the length here? Well, this length here is going to equal to the R here times the length of the W each cell. And however, now you can see the W equal to 2 divided by the square of the norm. And then you're going to times W here. And then you conclude that the margin here is going to be equal to 2 divided by the norms of W. Okay? So that's the key things we want to talk about. So that's what we talked about so far here. The margin here is equal to this quantity. Okay. All right, so that's the math we're going to talk about so far. And then once we have these guys here, and we are almost done here. So, well, so what we want to do now is this. We know how to measure the distance between these two boundary planes of that. And then we can formulate a new model, try to learn the parameters of this linear classifier. I want to push this boundary as far as I can, But at the same time, I want to make sure that the data points here are correctly separate, which means they are above this plane and below plane for the other class labels. For these reasons here, what we can do is to do this, right? So I'm going to maximize the margins. So maximize the margins. At the same time, I want to make sure that for all the data points here, it can be separated here. So for that reasons here, I'm going to formulate this as an optimization problem. I'm going to maximize the margin. Remember the margin, let's rewrite it again. So margin equal to 2 divided by the norms of W. So remember that's the margin we calculated here. So in order to maximize the margin, suppose I want to maximize the margin over all possible choices of W and B. So that means is equivalent to minimize the norms W squared of that. So you can see that's the case because margin is 2 over W, the norm of W. And then maximize the margin is equivalent to minimize the square of the norms of W. And so that's the equivalent statement of that. So if you understand that, and then we are all set. And then say I'm going to formulate this models here to something like this. So instead of, so we're going to minimize this norms of W here. So this is norms W. At the same time, subject to a set of constraints here. So these are the constraints. So constraint this. If your label is +1, so we want that data to be above these planes here, and that which means W dot xi plus b has to be greater or equal than 1. On the other hand, if your data here is a negative label, which means on this side here, and that means your data has to be less than -1 because below this plane here. So on the right side has to be this side here, and the blue here has to be on this side here. And these are the constraints of these models here. Okay, so let's think about it. Let's rewrite it again because I don't want to overwhelm you here, but let's rewrite what we talked about so far. I just want to wrap up with this. You can think about it here. So again, so the data we have here, let's revisit that, is xi and yi here. So that's data we have, and now is I goes from 1 to n. So m here. So this data set here, and the xi here is still would be n-dimensional, and the yi here. So now I'm going to use these notations of -1, 1 to enter the labels of that data set. So this is binary classification problem. And the model now is this. So again, the model is going to be W dot X plus B here. So that will be response here. And if this guy here is greater than 0, and then your predicted label is going to be 1. If it's less than 0, your predicted label is going to be -1. So that's the same as what we did previously. The same as previous here. So that's nothing new here. And however, the learning process now is different here. In particular, the loss function is different here. Well, in this case here, the optimization problem is the formula is this. You say, I'm going to minimize loss function. In this case here, the loss function is simply the norms of W here. And what this just means that if you do I equal to 1 and here, Wi squared, and that the norm is W. And minimize over all choice of W and this bias term V here. And that's the same. However, there's a key difference from this and the previous, because there is this constraint. You have constraints we have to satisfy. Subject to a set of constraints. What are the constraints? The constraint is the W times Xi, Xj here, plus B need to be greater than 1 if your label J is equal to 1. So if it's above that plane, you want to make sure it crosses the boundary, separating boundary there. And your W dot Xj plus B has been less than -1 if your Yj is equal to -1 on the other side. And that is the new model we're going to deal with. You can see it's different from the previous model. So the difference here is this. And this problem now is called a constraint optimization problem. So in this problem here, we want to minimize these guys here, but in this case, we're not trying to, when we minimize here, we're not allowed to choose any B and W and B, but instead, the B and W and B here has to satisfy these conditions first. This condition has to be satisfied. Essentially, we're saying within those conditions, within the space satisfied this condition, we're going to pick up the W that is smaller norm of that. So that is constraint optimization problem. And the question is, how do we solve this constraint optimization problem? And that's something we're going to talk about in the next lecture. But for now, I just want to kind of give you this framework of the SVM here. You try to, the framework, in many cases, is called margin maximization. We're going to maximize the margins of these two separating hyperplanes in the higher dimensions there. All right, so I have like 1 minute to see if you guys have any questions here.
Yes, one question. Will these lecture slides be on the midterm up to this point?
Oh, that's a good question. So the so the midterm is going to be so what day is midterm again? So
The 11th, I believe.
11th, right? So as I said, it will be possibly including today's lecture. So which means we're included it. So we haven't finalized the midterm yet. I think probably what this means, I think we will include anything up to today's lectures, including today's lecture.
So everything up to this exact point, like this fraction of these lecture slides that we are in.
Correct. But that's right. Well, up to this point here, because the lecture slides will have other materials, but again, up to this point here.
Got it.
All right. So with that, so that seems like that's it. Do you guys have any other additional questions? All right. Well, there's something to think about because, as I mentioned at the beginning, so this SVM involved a little bit more math here. So we'll go slowly. If you have any questions, so I don't need to go through them very quickly. You're welcome to stop me at any time. We'll revisit this again next week, next month. All right. Thank you, guys. Have a good evening.